Hi everyone, what's up? Welcome back to my tutorial channel. It's Daniel here, and today we will be talking about inferences on two symbols. And the first part today will be how to compare the means for independent symbols. So in this part, first of all, I'm going to show you what is the difference between independent symbols and pair symbols. And then we will focus on how to make a test for independent symbols. In the next video, I'm going to show you how to run a test for pair symbols. And finally, I'm going to show you how to do the conference intervals. Alright, so first of all, how to tell whether two symbols are independent or pair symbols. Let's go over this situation. How can we tell whether a new drug reduces blood pressure better than an old one? A drug company has developed a new drug that is designed to reduce high blood pressure. The researchers wish to design a study to compare the effectiveness of the new drug to that of the old drugs. So this situation, we want to compare the new drugs and the old drugs to see whether the new drug is effective. So we will have to find a way to compare one symbol using new drugs and one symbol using the old drugs to see whether the means are different or not. So we will end up have two designs. The first design is we will have to collect two symbols. And when two symbols are chosen, one will be assigned the old drug. This is the design one. And one is assigned the new drug. And then we compare the means of the two symbols. If they are different, that means the drug was effective. Otherwise, it's not effective. For the design 2, we will not have to choose two symbols. We should have to collect one symbol. So only one group of people will be chosen. They are given the old drug for a month. Then the blood pressure are measured, and then we give them the new drug for another month, and then their blood pressures are measured and recorded in the symbol 2. So if you look at here, suppose the symbol consists of 5 people, A, B, C, D, E. For the old drugs, we use the same 5 people, A, B, C, D, E. And for the new drug, we use the same 5 people. You see that? The old drug and the new drugs. So when we compare them, when we compare the old drugs and the new drugs, we are basically compare individual with individual. So we have to compare A with A, B with B, C with C, D with D, E and D. We're not going to compare the blood pressures of person A in the old drugs with person B in the new drugs. We have to compare in the exact pair, in the same pair. Go back to design 1. For the design 1, we don't care about the individual. We basically take the means of the whole symbol 1 and compare with the mean of the whole symbol 2. So that is the difference between design 1 and design 2. Design 1, we compare the mean of symbol 1 with the mean of symbol 2. This is independent because there is not a specific way to pair one person in the first symbol with one person in the second symbol. However, for design 2, it's clearly shown that we have only one unique way to pair the first symbol and the second symbol. Here A has to be paired with A, B has to be paired with B, C has to be paired with C, D has to be paired with D, and E is paired with E. So that is the difference between these two designs. Now we go to the more precise definition of independent symbols and pair symbol. For independent symbols, two symbols are independent if the observations in one symbol do not influence the observation in the other. And for pair symbol, two symbols are paired if its observation in one symbol can be paired with an observation in the other. Typically, the symbol consists of pairs of measurements on the same individual or on pairs of individuals who are related, such as husband, wives, or brothers and sisters. And for in this course, for independent symbol, if we want to test the difference between two symbols, we have to use two symbols, z-test or t-test. Z-test is used when the population innovation is known, and t-test is used when the population innovation is unknown. For pair symbol, we will have to use z-test or t-test. For pair symbol, we will get to know how to test pair symbol in detail in the next video. In this video, we should focus on independent symbol, how to run the two symbol z-test and t-test. However, using z-test is not recommended because in the real life, usually we don't know the population innovation. So the more applicable methods should be t-test. So for independent symbol, we are going to use two symbol t-test, and for pair symbol, we are going to use t-test. So in this video, I'm going to focus on the two symbol t-test. So mean compare test for independent symbol. Before we step into how to do the test, we have to get to know some notation. Here, when we want to compare two populations, the parameters are mu1 and mu2. Mu1 is the mean, the population mean of the first population. Mu2 is the population mean of the second population. The symbol means here x1 is the mean, x bar 1 is the mean of the first symbol, which is collected from the first population. And x2 is the symbol means of the symbol 2, which is collected from the second population. And the population's innovation is sigma 1, sigma 2. Symbol's innovation is S1, S2. Usually sigma 1 and sigma 2 are unknown. And the symbol size here is N1 and N2 for symbol 1 and symbol 2. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 notation here. Before you do any hypothesis testing, you have to define the null and the alternate hypothesis. The null hypothesis says that the population means are equal. That means mu1 is equal to mu2. And there are three possibilities for the alternate hypothesis. It's just similar to the hypothesis testing in topic 8. So here we also have two tail, left tail, and right tail. If we got mu1 is not equal to mu2 at the alternate hypothesis, this is two tail. This is two tail. If we have mu1 is strictly less than mu2 in the alternate hypothesis, this is left tail, and the last one, mu1 is strictly greater than mu2, is right tail. Before you do any test, you have to define whether it's a left tail test, right tail test, or two tail test, because it will affect the p-value and the critical value at the end. And when you run a test, the first step is try to summarize the question using notation. The second step is to define the hypothesis, the null hypothesis, and the alternate hypothesis. And the next step, you have to compute the test statistic. No matter if you are using the critical value or the p-value method, you have to compute the test statistics. So here the test statistic is basically the point estimate over the standard error. The point estimate here is measure the difference between the difference in the sample mean and the difference in the population mean. So it is x1 bar subtract x2 bar subtract the difference between mu1 and mu2. The top everything Everything at the numerator is called the point estimate, and everything at the denominator is called the standard error. The standard error here is square root of s1 squared over s1 n1 plus s2 squared over n2. And the degrees of freedom, actually for the degrees of freedom, since here we don't know sigma, so we have to work with student t-distribution. And remember, whenever you work with student t-distribution, you have to define the degrees of freedom. And for the two independent sample, we actually have a more accurate formula to compute the degrees of freedom. However, that formula is too complicated to be used. So for convenient purposes, we use this simple formula to find the degrees of freedom. So in the simple formula, we find a minimum between n1 subtract 1 and n2 subtract 1. For example, if the first sample, the sample size is 60, and the second sample, the sample size is 50, then we take the minimum of 60 subtract 1 and 50 subtract 1. So that's the minimum between 59 and 49, and it should be 49. That's how you find the degrees of freedom for a hand computation. If you compute if you run the test by hand, you should use this degrees of freedom. Of course, when you use software technologies to find the degrees of freedom, or the test statistics, or run the test, they will give you slightly different answer, because the computer and the calculator are set up to find the degrees of freedom using the more accurate degrees of freedom. Alright, next, mean compare test for independent sample. Remember, for any test, you have to check the assumption to see whether the central limit theorem is applicable. The first assumption you need to check for the two sample t-test is we have simple random sample from two population. Simple random sample, in chapter 1, I mentioned a simple random sample is a sample that is withdrawn in such a way that any sample will have equally likely chance to be withdrawn. And the second assumption is the samples are independent of one another. And the last assumption is its sample size is at least 30, or if the population is approximately normal by itself, you don't need the sample size to be at least 30. I repeat, for central limit theorem, if the original population is approximately normal, we do not need the sample size to be large enough. Even the sample size is just 2, the central limit theorem is still applicable. But if the population is not normal by itself, then we need the sample size to be at least 30 to make sure the central limit theorem is applicable. And once the assumptions are met, we can process our test. And for any hypothesis testing, we have two methods, the Pvalue method and the critical value method. These two methods will give you the same decision. It just depends on which methods you want to go for. Usually for technologies, for computation, for technology, they like to go for the Pvalue method. So once you already have the test statistic T, you have to look back to the hypothesis to see whether the test is in left tail, right tail, or two tail. If the test is left tail, the way you compute the p-value is the area under the curve of the student t-distribution with degrees of freedom computed to the left of the test statistics. And the right tail, the p-value is the area to the right of the test statistics. And the two tail, you will have to double the test statistics, one negative and one positive. So the p-value is the area to the left of the negative test statistics together with the area to the right of the positive test statistics. And if the p-value is less than the significance level alpha, then we reject the null hypothesis. Otherwise, we do not reject the null hypothesis. This is old knowledge, right? For the critical value method, we have to first define the critical value and then define the critical region. For the left tail, the critical value is of course a negative number, and it should be minus T alpha df. So the critical region is the area to the left of the critical value. For right tail, the critical value is T alpha df, and the critical region should be on the right of this critical value. For two tail, it should be on the left of the negative critical value and on the right of the positive critical value. So after you have the critical region, we reject the null hypothesis if the test status is in the critical region. Here again, the critical region here is basically the rejection region. It's just another name of critical region. Critical regions is the rejection region. Alright, here I have the picture here for you to compare. First, the critical method. Many times people will get confused between the three tests, left tail, right tail, two tail, and also some will be confused between the critical method and the p-value method. So here I have to include the 6 picture of the p-value method and the critical method to compare. So here, let's look at the first method, the critical region. For the critical methods, we have to find the critical value and the critical region. If you have left tail, we want to make sure that there is a tail of alpha area to the left. If you are working with the right tail, we want to guarantee that there is a tail with area alpha on the right side. And if you are working with two tails, we want to make sure that we have two tails equally, one on the left and one is on the right, and they have the same area of alpha half. So the critical value for the left tail test is a negative number, and that is minus T alpha. The critical value for the right tail test is a positive number, that is T alpha. And for a two tail, we have two critical values, one is negative and one is positive. For the left tail, the critical region is on the left of the critical value. For the right tail, the critical region is on the right of the critical value. And for two tail, the critical region are two side on the two outside of the interval formed by the two critical values. For the p-value here, the p-value, we have to compute the test statistics. For the left tail, the p-value is the area to the left of the test statistics. For the right tail, the p-value is the area to the right of the test statistics. And for the two-tail test, the p-value is the sum of the errors in the two tails. You see it? And if you compare between the critical method and the p-value method, you see here on the critical methods, on the picture, you have to mark minus T alpha, but on the p-value methods, you have to mark the test statistics. Here, T is the test statistics, and T with alpha, whether it's negative or positive, alpha or alpha half, this represents the critical values. You see that? So make sure that you have the right picture on the test if you choose critical methods or p-value method. Alright, so now we are going to perform a test one by one. First, in order to perform a two-sample t-test by the critical value method, we have to state the null and the alternative hypothesis. That is the first step. This step is important because we need to see whether the test is left tail, right tail, or two tail. Step 2, we have to choose a significance level alpha and then find the critical values. Usually the significance level will be given on the test. However, even if it's not given, we usually take alpha is equal to 0.05. because remember, an event is called unusual if its probability is less than 0.05. That is where the 0.05 comes from. Step 3, we have to compute the test statistics. Not even for critical method, for p-value methods, you also have to compute the test statistics. And the test statistic here is t. The reason why we use t, not z, is in this problem, sigma 1 and sigma 2 are not given, and we are working with student t distribution. That's why we have to use t to represent the test statistic. So the test statistic is the point estimate over the standard error. The point estimate is the difference between the difference in the sample means and the difference in the population mean. And at the denominator, we have the standard error. The standard error SC is equal to square root of S1 squared over N1 plus S2 squared over N2. And the degrees of freedom is the minimum between N1 subtract 1 and N2 subtract 1. Here's the thing. Usually, the more accurate formula to find the degrees of freedom is not this formula. However, for convenience, we choose this this easy formula because it's good for hand computation. And because even though the p-value and the test statistic might be a little bit different, however, it doesn't affect the decision of the test. Step 4, we have to determine whether we reject the null or do not reject the null hypothesis. So it really depends on whether the test is left tail, right tail, or two tail. If this is a left tail, if we are dealing with left tail test, the critical value should be negative, and it should be minus t alpha df. That means we have to have an area of alpha on the left of the picture, on the left tail of the picture. And the critical region is on the left of the critical value. So if the test statistics falls into the critical region, we reject the null hypothesis, and it means that t is less than or equal to negative t alpha df. If the test is right tail, the critical value is positive, and the critical region should be on the right side of the critical value. So we reject we reject the null hypothesis if the test statistics is greater than the critical value. That means on the right side of the critical value. If we are dealing with two-tail tests, we will have two tail on the picture. One is on the left of the positive critical value t alpha half df. One is on the right. One is on the right of the positive critical value, and one is on the left of the negative critical value. And if the test statistic falls into the two-tail outside, we reject the null hypothesis. If the test statistic falls into the middle region, then we do not reject the null hypothesis. Simply, if the test statistic falls into the rejection region, we reject the null hypothesis. Rejection region here means the critical region. And this is the opposite with the acceptation region. And step 5, we state conclusion. So that's how we perform a two-sample t-test by the critical value method. Now for p-value methods, the first step, we also have to state the null and the alternate hypothesis in order to define whether it is a left tail test or a right tail test. And then if we make a decision, we have to choose significance level alpha. Again, if it's not given, we take it 0.05. Step 3, we have to compute the test statistic and the degrees of freedom. And step 4, we have to compute the p-value. So for the left tail, the p-value is the error to the left of the test statistics. For the right tail, it is on the right of the test statistics. And for two-tail, we have to make one negative test statistic and one positive. So the p-value is the error to the left of the negative test statistics and on the right of the positive test statistics. And we can double region because these two regions are equal. And if the p-value is less than alpha, we reject the null hypothesis. Otherwise, we do not reject it. Finally, the last thing I want to talk about today is how to construct the 1 minus alpha conference interval with independent symbols. So in order to construct the conference interval for independent symbols, the first step we have to compute the symbol means 1 and symbol mean 2, and also define the significance level. So the point estimate here is x1 bar subtract x2 bar. Step 2, we have to define the degrees of freedom. Here we can use minimum of n1 subtract 1, n2 subtract 1. We don't need to use the accurate formula. Step 3, compute the standard error. And don't forget the critical value. The critical value here, T alpha half df, because we want to bound the middle alpha region. So the sum of the two tails should be alpha. The sum of the two tails should be alpha, and its tail should be alpha half. I repeat, we want to have 1 minus alpha in the middle, so the sum of the two tails should be alpha, and its tail should be alpha half. The standard error should be square root of s1 squared over n1 plus s2 squared over n2, and the margin of error is the product of the critical value and the standard error. And then to construct the CI, we take the point estimate, subtract the margin of errors to find the lower bound of the critical of the constant interval, and we take the point estimate plus the margin of error to find the upper bound for the confidence interval. So let's go over the practice. That is everything for today. Now let's go over some practice. Example 1. The National Assessment of Educational Progress (NAEP) tested a sample of students who had used a computer in their mathematics classes and another sample of students who had not used a computer. The sample mean score for students using a computer was 309, with a sample standard deviation of 29. For students not using a computer, the sample means were 303, with a sample standard deviation of 32. Assume that there were 60 students in the computer sample and 40 students in the sample that hadn't used a computer. Can you conclude that the population mean scores differ using alpha is 0.05 level? So first and first, we have to summarize the question using the notation. It should be easier for you to solve the problem if you mathematical modeling this problem. If you're mathematically modeling this problem into notation. Other question, I have highlighted some important figures. You see that the first number is 309, and it's talk about the sample mean for people who using computer. Assume that is the first symbol. So 309 here is basically x1 bar. You see that? And then with a sample standard deviation, we are talking in this about the same symbol. And they give you the sample standard deviation, not population standard deviation. That means sigma 1 is not given. We should know S1 is 29. And for students not using a computer, the sample means were 303. This talks about the sample means of the second sample. With a sample standard deviation of 32, this talk about S2, the second sample standard deviation. So that's why we have S1 29, S2 32, X2 bar is 303. And they also say that assume there were 60 students in the computer sample. That means N1 is 60, and 40 students in the sample that hadn't used a computer. That means N2 is 40. Can you conclude that the population mean score differ? Differ here mean not equal. So it's clearly show this is two-tailed test. We see it. Use the alpha level 0.05. So here I have alpha 0.05, and the test. To run the test, no matter you using the p-value methods or the critical value methods, we have to define the null and the alternate hypothesis first. So the null here say that the two population mean are equal, and this the alternate hypothesis says that the population mean are not equal, they differ. So x0 is mu1 is equal to mu2, and x1 is mu1 is not equal to mu2. Here we assume symbol 1 is the symbol of student who using computer, and the symbol 2 is the symbol of student who didn't use a computer. And this is two-tailed. Alright, so this is the summary of the last problem. I have already summarized the question using the notation. This step is called mathematical modeling. That's how we model the problem into math notation. Alright, the test statistic here is t is equal to 0.9533. If you don't know how to compute the test statistics, please rewatch the slide that I show you how to compute the test statistics. There is a formula to compute it in my video. And the degrees of freedom here is the minimum of n1 subtract 1 and n2 subtract 1. n1 subtract 1 here is 59 and n2 subtract 1 is 39. So the minimum is 39. And we can perform the test either by the critical value method or the p-value method. Here in the critical value methods, we have to first define the critical value. This is a two-tailed test, so we should have two critical values. One is negative and one is positive, and we expect to have 95% in the middle, so we have 2.5% on the left tail and 2.5 on the right tail. Using degrees of 39 and the 2 and t distribution table, we have the negative critical value should be negative 2.02 and the positive critical value should be 2.02. And the critical region should be the shaded area here, that means the two-tail area. So it should be on the left of the negative critical value and on the right side of the positive critical value. Next, we notice that the test statistic here, which is 0.9533, is in the middle. It should be somewhere in the middle between negative 2.2 and 2.2. That means the test statistic falls into the exception region and does not fall into the critical region. So we do not reject the null hypothesis. That's how we run the critical value method. Now for the p-value method, we have the test statistic here is 0.9533. So we mark it on the picture, and its negative should be negative 0.9533, which should be here. And the p-value is the sum of the areas in the two tails, so it should be 2 times probability that the student t distribution variable with degrees 39 is greater than 0.9533, and the p-value is 0.346, which is a lot greater than 0.05. So here the p-value is greater than the significance level. That means we do not reject the null hypothesis. And by comparing these two methods, you see that no matter which method you use, you should have the same decision. In conclusion, we conclude that there is not enough evidence to conclude that the population mean scores differ. Or we can say there is insufficient evidence to conclude that the population mean scores differ. Next, I'm going to show you how to perform two-sample t-test by TI84 Calculator. So first, I'm going to reshare the summaries of the last problem. Here we have all the information here. And now let's follow me. First, you press the Start button on your calculator. It should be under Delete. So when you hit on Start, there are a couple of options on the top. There are 3 options: either Edit, Calculate, or Test. Please choose Test, and when you click on Test, there are a couple of options. There is a list of couple options. I want you to go for option number 4, two-sample t-test, and then they will ask you to choose whether you enter data or stat. If you have a data set, you can enter the data set, but here this problem gives you the statistics, so you have to choose statistics, and then they will ask you to enter x1 bar, that is 309, s1 is 12, n1 is 60, x2 bar is 303, s2 is 32, n2 is 40, and the test here is two tails, so you have to choose the first option, mu1 is not equal to mu2. And then at pull or unpull, please choose no unpull. The pull test is not recommended. And once you do so, you have this is the result. The test statistic is 0.9533, which is close to the test which is exactly the test that we computed by him. The p-value is 0.3434. This is exactly the p-value that I showed you from the last show. The degrees of freedom here is not 39, you see that, because here for the calculator they use the more accurate formula to compute the degrees of freedom, not using the convenient formula. And we have the sample mean 1 is 309, sample mean 2 is 303, the sample standard deviation of the first sample is 29, of the second sample is 32. You see that, and you can roll all the way down for more statistics number. And we see because the p-value here is greater than 0.05. You see the p-value here, p is equal to 0.3434, which is greater than 0.05. So we do not reject the null hypothesis. That means there's not enough evidence to conclude that the population mean score differ. So that's how you run the test. Now we go to the last topic of today, the last point of today, how to construct the confidence interval for two sample means difference. So let's look at this example. Example 2, a drug company has developed a new drug that is designed to reduce high plus ratio. To test the drug, a sample of 15 patients is recruited to take the drug. Their systolic plus ratios are reduced by an average of 28.3 millimeters of mercury with a standard deviation of 12. In addition, another sample of 20 patients take a standard drug. The plus ratios in this group are reduced by an average of 17.1 with a standard deviation of 9. Assume that the plus ratio reduction are approximately normal distributed. Find a 95% confidence interval for the difference between the population mean reduction for the new drug and that's of the standard and that of the standard drug. I have already highlighted the important figures, like 15 is the first sample size that is in 1. 28.3 is the average of the first sample, which means x1 bar. 12 is the sample standard deviation, which is s1. 20 here is the sample size of the second sample, so 20 is in 2. 17.1 is the average of the second sample, so this is x2 bar. Sample standard deviation from the second sample is 9, so it's s2. And we want to construct the 95% CI for the difference. Alright, so here don't forget that we have an assumption that the plus ratio reduction are approximately normal distributed. This means that the central limit theorem is applicable. So for summary, we have the first sample mean is 28.3, second sample mean is 17.1. The first innovation sample is 12, the second sample innovation is 9. First sample size is 15, second sample size 20, and significance level is 0.05. And now we find the CIs. So remember the CI is the point estimate plus or minus the margin of error, and the margin of error is the standard error times the critical value. So here first we find the point estimate by finding the difference between the two sample means when we got 11.2. Standard error is easy, just standard error is square root of s1 squared over n1 plus s2 squared over n2, which is 3.69. And the CV here, the critical value, we are working with student t distribution, so we have to define the degrees of freedom. Again, we have a more accurate formula to find the degrees of freedom, however, it's too complicated, so for convenience, for convenient purposes, we use this formula to find the degrees of freedom. So degrees of freedom here is 14. And the critical value here is 2.14. So the margin of error is the product of the critical value and the SC, the standard error. So the margin of error is 7.9. The 95% CI is the point estimate plus or minus the margin of error. So we got 11.2 plus or minus 7.9, which is 3.3 to 19.1. And our conclusion is there is 95% chance that the true difference between the means is between 3.3 and 19.1. This is the theoretical way to find the critical value. And by calculator, on TI84, we can use the two-symbol t interval on TI84. So we go to stat, choose test, and go to the option two-symbol interval at option 0. And then we enter all the information S1, X1, S1, X2, S2, N1, N2. And don't forget to choose unpool. And then we have the interval here is 3.59.12 and to 18.8. From the last methods using from the theoretical method, we got this is 19.1, but here we have 18.8. The reason is because we have slightly different degrees of freedom. The most accurate degrees of freedom is this formula. However, in practice, we don't need to use this formula, but on the calculator still count this formula to compute the degrees of freedom. And the conclusion is there is 95% chance that the true difference of the means is between 3.3 and 19.1. This is how we use two-symbol t-test and two-symbol t-interval for the two-symbol means, and assume that we're not working with pool symbol because pool symbols are not recommended. Alright, so that's it, everything of today. Thank you so much for watching my video. I will post my next video sometime next week. Thank you. Bye bye.